Hello.
And especially Dr. Pawan Kumar Arora sir and Dr. Yogesh Srivastav for having invited me to share my views on this important topic. Let us begin with the presentation. I'm just sharing my screen.
Hello, sir. Sorry, sir.
I'm fine. Visible to everyone. Okay. Not this picture in picture.
कोई भी बच्चा अपना माइक ऑन नहीं करेगा तो मोबाइल फोन को लॉगिन नहीं करेगा किसी बच्चे के अपने आवाज आ रही कुछ है
Anyone can, so the topic talk is medical and of additive manufacturing. Items are mentioned here. First, we'll go for a brief introduction to additive manufacturing, state of the art in medical and medical additive manufacturing. Talk about 3D printing, 3D going on at JP University, Guna. After that, there will be question and answer session. So anyone have any query, then he can ask that. Begin with additive manufacturing. I am sure that you might have uh, known about additive manufacturing so far. In a 3D printing technology that is capable of fabricating physical parts directly from CAD model data by depositing material in layer by layer fashion, as you can see here. Some of approach as against to the conventional manufacturing processes you can see on the screen. I'm not taking much time on this because I hope you might have gone through all these things the previous lectures. So initially we must have a 3D CAD model in order to print a 3D part using 3D printing technology or additive manufacturing technology. Then that CAD model can be created using any of the software like SolidWorks or ProE or AutoCAD, etc. Or even CT scan data can also be used to create a CAD model or MRI scan data. So these MRI scan data and 3D scan data are very important as far as medical and biomedical area is concerned. So and once we have got a 3D CAD model, then we have to convert that into STL file. That STL file is converted into sliced model. Then one slice at a time is given to 3D printing machine and physical part is realized in this way. After that, if then post processing may also be performed. Why additive manufacturing is such a big deal nowadays? So we all know that additive manufacturing launched in 1980s, but it has got momentum in after 2010, right? Technological advancement that took place in previous decade that has been responsible means the powerful softwares which are capable of generative design and topologically optimized design. So because of that, 3D printing technology has gained very popularity in the market. Then there is a growing range of printable materials there to operate due to patent. Many of the processes has got out of the um, patent policy because after 20 years the patent has been expired for most of the technologies and the government and industry has also been taking many initiatives to promote this technology. So these are the key behind this popularity of 3D printing technology. The strong feature, if we talk about, then it has got a great design flexibility. As you can see on the screen, no matter how complex part is, there is nothing like complexity for this technology because it prints one layer at a time. So complexity is nothing for this technology. Then secondly, it can print multicolor and multi-material parts for demonstration purpose especially. Then no assembly is required. As you may be aware that not required means assembly is required only at the CAD modeling stage. In itself, we can perform assembly and then that can be printed as a single component. Then no tooling is also not required in this 3D printing technology. Then another feature of this technology is mass customization. As opposed to our mass manufacturing or mass production, this technology provides the feature of mass customization. That means the manufacturing cost, as you can see on the screen, manufacturing cost that doesn't go up with increasing complexity or increasing number of or increasing complexity or customization. Means if there is one part or if there are 10 parts or 100 parts or 1000 parts, the cost per part remains same in case of 3D printing technology. And another strong feature is it supports generative design. Generative design is basically computer-based method, we can say, that focus on the creating multiple designs of a given part. To provide a design space to the software, and then we have to provide the various constraints that are applicable there, and then we give the load or pressure, whatever it is, and material properties, etc. And software generates multiple design options for us depending on our objectives. So that kind of facility is now available in CAD modeling softwares like Fusion 360 or the SolidWorks. So that kind of facility is available. So using that, this feature, we can generate topologically optimized components which is mainly focusing on minimization of the material. Means where material is required, only put material there, otherwise remove the material without sacrificing the uh, mechanical property of the. So you can see here that traditional CNC machine, we can create this kind of part, but with the help of additive manufacturing technology, we can produce this kind of part without sacrificing any mechanical performance of the. Initially weight was 1.2 kg, whereas now the weight has reduced to up to 0.7. So we have optimized the material utilization, and that has become possible because of the availability of that capable software as well as 3D printing technology. So these are the features of this technology. Then there are mainly 7 categories of additive manufacturing technologies. So additive manufacturing is basically an umbrella term, right? Which encompasses different processes under these 7 categories. Wet photopolymerization is the first one. So that is basically liquid-based process, and this is based on the photopolymerization principle of the UV lights. So the part is, once the CAD model, one file at a time is given to the machine, and one layer is printed onto the platform, then it goes down, and again the liquid gets solidified. This way, part gets fabricated. Wet photopolymerization process. Then second process is binder jetting. That is powder-based process basically. In this process, a liquid binder is used to cure the raw material or powder material as per required. Another process, then extrusion is the other category of the 3D printing technology. Wire is used in form of filament. Means material is used in form of filament, as you can see on the screen, and filament is extruded through the one extruder head, and it gets melted inside this extruder and simultaneously gets printed onto the substrate. So it works like that. Then another is powder bed fusion, which is again based on the powder material. And in this process, a laser source is used, laser beam is used to cure the, or basically sinter, you can say sinter the powder material. So this technology is available for powder, metallic powder as well as polymer powder. And even for ceramic material also, the bed fusion process is available. Right. This one, directed energy deposition, is the most advanced additive manufacturing technology available today. So in this process, raw material is used in form of powder. There, in this process, there is no bed actually. Bed of powder is not there. Instead of that, powder is impinged onto the substrate is, and when it is required, and simultaneously it is cured by the laser beams. A laser beam is there, is centrally laser beam is there, and four or five annular path are there through which powder is dispensed as per the requirement. So uh, this is slightly different from the powder bed fusion because it does not have any powder bed there. So it requires less amount of powder material while printing some component. Major seven technologies I have quickly shown you. Now we will move towards the medical and biomedical applications of the additive manufacturing. The broad applications of medical and biomedical area of 3D printing or additive manufacturing can be classified in these categories. Like first one being the medical anatomical models, then there may be patient-specific implants, then prosthetics and orthotics. Then next one is customized tools and surgical guides, health monitoring and drug delivery devices, tissue engineering, and bioprinting. So these are the broad areas wherein additive manufacturing technology is being utilized. So let us see the medical anatomical models first. So basically, anatomical models are printed by using 3D printing technology, are used for basically two purposes. First one is education purpose, and second may be for surgery planning and training. In especially in medical area, we are talking about. So while we talk about educational purpose, then okay, so suppose traditionally anatomical models are usually what happens. Why suppose there is medical college or something like that. So for training purpose, they require anatomical models. So they are usually obtained from either cadavers or from they are created by the other processes, but they are very expensive and difficult. And more importantly, if we are creating them using the some or other process, then it is very difficult to obtain the customized shape of the models. So 3D printing is a perfect solution for this. So here we can see some of the examples of the models that are being used in educational for education purpose. So here you can see specific uh, foot model, then this is skull model, spine model, model of a spine, then this is the heart model, this is bone, a femur bone. So this kind of models can be printed using additive manufacturing process. Of course, if you want to print a customized item, then we have to go through a specific process that I will show you a little later, right? Then, if we talk about pre-surgical planning and training, these anatomical models is for patient-specific implants and surgical guides. Then, they are very good for surgeon manufacturer communication tool, and they are also very good for communication between surgeon and patient. So what it mean actually? Suppose um, surgeon using these kind of models, surgeon can communicate exact requirement of their to the manufacturers via this kind of model what actually they want to fabricate or what kind of implant they require exactly, right? And also this kind of model is very much helpful to communicate with the patients, to explain the patient their case, what is going on internally inside their body, patient's body, what problem lies there, and how they can correct it. So they can create such kind of models using 3D printing or additive manufacturing technology, and they can explain it very well to the patients. So patient becomes very comfortable and comfortable with the doctor. Okay, okay, doctor, what is doctor is saying, he may get very clearly. So here you can see some model. This is mandible fracture fixation. So this is actually the CAD model of the mandible of the patient, and then they have fixed this broken mandible with the help of some fixing plates. So this kind of model they can show to the patient as well as the manufacturer what exactly they require, and they are the measurement, exact measurement of the this kind of plates they can communicate to the, like this, suppose mandible is broken or the some cranial implant is required, that what is cranial implant and how and what procedure they have to undergo to fix this kind of cranial implants. So they can explain very well using this kind of models. Apart from this, they use this kind of anatomical models for surgical planning and training. Like this is a very renowned case study. They are the twin joint babies, as you can see on the screen. So this was very complicated case. This is available on Google as well. You can search it, twin joint babies. And read actually in this case, they just CT MRI, they just got MRI done, and then they printed uh, a, a soft model using this. They also created a virtual model or CAD model of the inside of the their head, and they studied the complications very rigorously or very seriously. They could understand the complexity of what is inside their different nerves are there, and where they have to perform a surgical procedure, how they will separate them out, right? That kind of planning they can do with their other doctors as well as their staffs, as well as they can also discuss with their patients, relatives or parents, etc. So that kind of exercise they have performed, and they actually performed the surgery on this additively manufactured model just to train themselves, just to make themselves comfortable and conversant with what is there inside their head. Okay, so this kind of exercise took them almost 5 to 6 hours less timing. So this operation almost took 13 to 14 hours instead of 20 to 21 hours. So this kind of pre-surgical planning they can plan in very complicated cases. The second case, the second area is patient-specific implants. This is very important nowadays. So what is medical implant? Basically, medical implants are devices or tissues that are placed inside the human body. The surface of implants that contact the body is made of a biomedical material such as titanium, silicone, etc. The example of patient-specific implants are artificial pacemakers, cochlear implant, cranial implant, bone implant, stent, dental implant, bone scaffold, etc. So different types of implants can be created. The more importantly, they can be customized, means individual. They can be customized to specific individual or specific patients. That's why they are being called patient-specific implants. So there are many benefits of this kind of patient-specific implants. Like first one being the surgery is quick, easy, and safe because everything is known in advance. Doctor has already customized the implant. What kind of implant? What is the anatomical shape of the implant, or what is the conforming surface of the implant? so that it can be fixed during the operation exactly as they want. So they create patient specific implants so they can very easily that inside the human body without any problem. Means they don't need to perform any kind of cutting or any type of modification at while patient is on the operation table. So everything is known them to in advance. So it is very quick, easy, and safe. Then secondly, aesthetically superb results are there. So what happens sometimes, suppose some cranial implant is required. So if that implant is specially designed for the specific patient, then that will conform to the anatomical shape of the patient's body. So that will not look anything any onto the patient. That will be conforming to his own anatomical shape, so that will look natural, right? Then reduced infection risk of infection reduces because the implant is customized one, so it does not take longer time during the operation. So less operating time means less chances of infection, and less and the patient also gets fast recovery as well. Peace of mind is again means doctors knows everything in advance, so there is no tension before the surgery. They know in advance what they are going to get inside the patient body wall while they will be making a cut on the operation table. Long-term costs are lower, especially in case of patient-specific implants, because they fit properly onto the anatomical shape of the patient body. If it is a own implant, then the implant will be very much conforming to the existing shape of the patient's bone. So there will be less chances of shielding effect, and there will be less chances of some local damage to the between the uh, bone and the implant, because it will be fixing properly, conforming exactly to the natural shape of their bone. So there will be less chance of second surgery or revision surgery. So that's why it is told that it is less costly in longer term. Nowadays, more than 95% of the hearing aids are being manufactured using 3D printing technology. Hearing aids. Here is another example of a specific load-bearing bone implant. This example of a cranial implant of a patient. They design a cranial. Suppose any human being met with an accident, and suppose some cranial is damaged, then some CT scan is performed, and then they develop a specific model like you can see here. So that is conforming to their head, uh, shape of their skull. So it will look natural to their face. It will right. How it is created, I am showing you just uh, one or two slide later. Then here is a hip socket, metallic hip socket. Then there is an example of titanium mesh heel, particularly from a patient who was having cancer in his heel bone. So his heel bone was removed through operation, and artificially developed, additively manufactured heel was implanted inside the body. Right. Then dental implants are also there. They can also be fabricated using 3D printing technology. So here is the process how we can create the specific implants. So suppose what happens initially, we go for CT or MRI scan depending on the patient's affected side. If it is brain or something like that, then we have the MRI scan. Otherwise, we can go for CT scan. CT scan are usually the hard bones, and MRI are usually for soft tissues. Better for soft tissues, they capture soft tissues in a better way. So that kind of test we have to go for, and that data is stored in DICOM file format. DICOM is basically um, a file format which is in medical science. So what CT scan or MRI scan data we see, they are actually printed only some 20 or 30 or 40 slice. It is a bunch of slices, more than 1,000 slices may be there, but doctor only prints the most important ones onto the film, right? So their file format is DICOM. Then that DICOM format has to be converted into STL file format. Is the file format, you may be aware about that manufacturing technology. So file format has to be converted into STL file format. Then we have to process STL file format into software for to correct any error. If there are some error, then we have to process that STL file before going for the printing to design patient specific implant. So this much portion is important for creating the model of the patient's affected body. Created the model of that. Suppose if we talk about this one implant, then first of all patient will be MRI scan or CT scan, because this is skull. So in this case they will go for the CT scan only. So they will perform a CT scan of the patient. So they will be getting this kind of image. They will be of course getting a CT image that will not be like this. So CT scan has to be converted using certain softwares are available like Invacilus or Doctor 3D or Mimics, like softwares are available. They can be used to convert the CT scan images into the STL file format. So they reconstruct the 3D volume using the CT scan data icon file, and they create a STL file. Once using that STL file, we can create the model of the. So we have created this skull up to this position. So we will create a CAD model, and then we will print the physical model of the patient's skull. Then in CAD model itself, we will design this implant onto this skull, damaged skull. We will remove the damaged portion in CAD model, and we will design this page, right? And once this page is designed in CAD model, then we will only keep this portion, the implant portion, the main skull, we will delete or we will remove this. So we will obtain this implant in CAD model. Model of implant is obtained once, then we can print it very well using any 3D printing technology. And once this is printed, because this is already conforming to the shape of the skull of a specific patient. We all know that the anatomical shape of the skull of every human being differs slightly from one to other. So this conforming is actually, this conformance is taken while in CAD modeling software. We actually reconstruct the left side of the um, we recreate that side in this side, right side. So it conforms to the left side of the. There is no mass here. Now it is broken. So that side of the skull is imposed onto this side. And then we create a patch using that shape. So that's why it conforms to the natural shape of the skull of a specific patient. And that can be printed using additive manufacturing technology. So at this stage, during conversion of this during conversion from the CT scan model or CT scan data to the CAD model, the role of a radiologist and clinician or doctor is very important, because they will help us identifying the exact region of interest. In this region of interest is very important. When we convert CT data into the STL data, then we have to choose, we have to apply certain Hounsfield units. Means according to the density of the bone or the soft tissue. So we have to choose which portion to keep and which portion is to remove. So at that stage, the expertise of a radiologist comes very handy. He'll exactly let you know that this portion is required, this portion is needed to be removed. Then only we will be able to get the exact CAD model of the patient's affected joint. Right. So after this, once we have designed the patient-specific implant, then we can proceed with two path. First one being the fabrication of implant prototype by RP approach. Rapid prototyping process may be used, means that is again 3D printing process only, but that is used for making a prototype only. First we make a prototype of that, and then using rapid tooling process we can print that prototype into the desired material actually. Right. Nowadays, the second path is usually taken because of the advancement in the technology. Nowadays, there are additive manufacturing processes which are capable to print anything in metal like titanium or the stainless steel or the chromium cobalt or whatever material. There are there are many materials available. So usually this route is not adopted nowadays. Directly we can print the specific patient specific implant using any of the process that we have seen so far previously. So usually if we want a metallic implant, then we usually go for the directed energy deposition or the um, powder bed fusion process. So these two processes are very capable of producing parts in metal. So if we want a titanium implant, then we can go for these processes. And then we have to validate and sterilize the implant, and then finally we can fix that implant into the patient's body. So this is how we can create an specific patient specific implant using additive manufacturing process. Here is the digital imaging and communication in medicine file, DICOM file is there. How CT scan takes place. This is an example. CT scan, while we perform CT scan, there is a X-ray source and there is a detector, and donut is there in the machine. If you have seen any CT or MRI machine, then a donut is there. So patient is inserted inside that machine. The affected zone is taken beneath that donut, machine is started. So X-ray um, X-ray beam of X-ray is collected by the detector on 360-degree like this. It keeps rotating like this, and it takes multiple images, two-dimensional images from different sections of the patient's affected zone, and it reconstructs those images to create a 3D volume. So that makes the 3D volume of the patient's affected area. So that can be visualized. Doctor usually, this is the CT scan like we see. Doctor, suppose we have taken this many images. A doctor prints only the most affected 30-40 slices onto the film, and they provide that in us to us in physical form. Right. So this is the Hounsfield unit I was talking about. Hounsfield unit is usually required while we are separating the mass from the soft tissues from hard tissues while converting CT scan into the STL file. So water is usually zero Hounsfield unit. Lungs, etc. are in has values in minus. Air is minus 1000 Hounsfield unit. Then kidney, cancellous bone is 300 to 400. Cortical bone 1800 to 200. 45 to 65. Converting, we have to apply, we have to insert this kind of into the software so that it separate out the cortical bone from other items, other means other soft tissues and all. Very important. Exact what that exact value we have to put Here we need expertise of a radiologist or a doctor. This is diagram viewer where we can see the reconstruct obtained from the CT scan data. Next area is prosthetics and orthotics. So prosthetics are basically the devices that replace the missing body parts, whereas the orthotics are devices used to modify the structural and functional characteristics of the neuromuscular and skeletal system. So basically, there are three things: implant, prosthetics, and orthotics. So implants are basically kept inside the human body, whereas prosthetics are useful to replace to support any missing body part. Suppose a person lost his lower limb, then artificial limb may be there. So artificial limb is basically a prosthetic device, prosthetics, and orthotic is basically used to correct some deformity or support some inability of the human being. So some example of the prosthetic like lower limb prosthetic or upper limb prosthetic, yeah, wrist prosthetic of any human being, right? Whereas the example of orthotics are different kind of braces, like you can see here. This is the brace. Then wrist splint are the spinal braces, right? So that kind of which supports our existing body part just to correct some kind of deformity or some injury. So they are orthotic, they are known as orthotics. So 3D printing or additive manufacturing also very much useful for producing customized prosthetics and orthotics. So traditionally, the methods of making prosthesis was very time consuming and very, we can say, cumbersome and painful actually. So traditionally, the patient has to visit doctor's clinic 3-4 times before his prosthetic is ready. So he used to visit his doctor's clinic, and then doctor takes they prepare a positive mold using the positive model using that casting. Then using that positive model, they used to create the socket for the um, lower limb. So that process is very painful. Sometimes dry and scaly skin is there. The patient has a risk of ulceration or infection, rashes, itching, etc. There are different risk in that, and this was very time-taking process. So now with the advent of these technologies, now we can club the 3D printing technology along with the CAD/CAM softwares, and we can create the this type of prosthetics and orthotics within very short span of time. So if we want to build some prosthetic or orthotic, then 3D scanner is used. 3D scanner is basically scans the surface of your body part, and it creates the point cloud data. Okay, here it is not there. So it creates point cloud data, and then using that point cloud data, we have to surface onto that using any CAD software. Once we fit the surface, then we can create a CAD model on CAD model of the same. Once CAD model is prepared, then we can directly print that CAD model using any of the 3D printing technology. So here are the examples of the some of the orthotics and prosthetics. Here you can see these all are additively manufactured prosthetic and orthotics. This is the example of lower limb. The socket is printed using the FDM process, SLS process, selective laser sintering process. Then ankle foot AFO is there, ankle foot orthosis. This is orthosis. And then custom made leg immobilization. Like this is wrist splint or orthosis. So, and here is another example of artificial limb made by process. Okay, exoskeleton by FDM technology. So this is basically made to provide support to the spine. If if there is some problem in his spine and the person is not able to stand straight, then he may require exoskeleton kind of thing which supports him. So that can be prepared, customized exoskeleton can be prepared using 3D printing technology. Right. Then the next topic is tissue engineering. Tissue engineering is basically an interdisciplinary field that applies the principles of engineering and life sciences towards the development of biological substitutes that restore, maintain, or improve tissue functions or a whole organ. So tissue engineering basically starts from the isolation of cells from the patient's body. If there is some patient, then we can regenerate the patient's body part using his own cells. That is the tissue engineering basically. So in the beginning, we have to isolate the cells. Basically, stem cells are required for this purpose. So stem cells are isolated from the human body. Then cell expansion takes place in the lab. Then there is 3D three-dimensional scaffold is required. So that 3D three-dimensional scaffold, that cells, isolated cells are seeded onto this kind of 3D scaffold. Then they are allowed to grow in presence of certain growth factors inside the laboratory or inside the body itself. And then if it is grown in laboratory, then it is implanted inside the human body at the end. If it is already inside the human body, then there is no need to implant it again. We first, so there may be two types of tissue engineering we may perform. One is in vitro and in vivo. So in case of in vitro cases, we isolate the cells from the human body and then we expand them in the lab, and then on 3D scaffold we seed that into onto the scaffold, and it grows inside the laboratory, and finally once it is fully grown, then that is implanted inside the human body in vitro cases. In vivo cases, what we do, we directly insert the scaffold inside the human body at the affected area and let the grow the bone cells or any other type of cells this scaffold. So after some time, patients recovers, and this cells grow completely onto this scaffold. So this way there are two ways in vitro and in vivo tissue engineering. So scaffold is, you can see the scaffold is very important link in this tissue engineering approach. Tissue engineering exists there for some 20-30 years, but the 3D printing came into existence in contributing in tissue engineering, especially for last 15 to 20 years, because it can produce customized scaffold, customized scaffold as per the requirement of the patient. That is why it is becoming popular day by day for making of scaffolds. So scaffold must have certain properties like they must be biocompatible, biodegradable, they must have adequate porosity and adequate mechanical strength and surface topography and chemistry. So because we are actually implanting this scaffold inside the human body, so it must be biocompatible and biodegradable. Biocompatibility is very much important. Biodegradable may or may not be. Sometimes biodegradable, they may be biodegradable or they may not be biodegradable. Right? If they are biodegradable, then it will degrade with over the time, means within a span of 6 months to 12 months, it will naturally come out of the body. Patients urine, etc., right, with the time. If it is non biodegradable, means if it is of metallic item, then it remains there inside the body, but it must be biocompatible. In both the cases, it should be biocompatible. And for scaffolds, porosity and mechanical strength both are very important, and there must be a good balance between the porosity and mechanical strength, because porosity is required for the cell growth as well as the nutrients migration inside the scaffold, whereas mechanical strength is required so that it can withstand the pressure of the cells, can withstand the pressure of the cell. So there must be a good balance between the porosity and mechanical strength. If we increase the porosity, then there will be mechanical strength will be reduced, and if we provide more mechanical strength, then there will be less porosity, and cell will not grow properly. So there should be a good balance between porosity and mechanical strength while we are developing any scaffold, porous scaffold. So here is the reason why 3D printing is becoming more and more popular for tissue engineering applications, because as I told you that this technology can get customized scaffolds. As you can see, here is an example of mandible. So a porous mandible has been created using 3D printing or additive manufacturing technology. Now this can be, here is another example of the external ear of the human being. So it is in customized shape. Now the human stem cells can be seeded onto this, and it is kept inside the bioreactor so that the cells grow and differentiates into the specific cells. And once it is fully grown and developed, then it is implanted inside the human body where it is required. Right. Bone tissue engineering have okay. Bone tissue engineering. Why? What happens? Bone in case of bone tissue engineering, there are basically these 3-4 methods are available nowadays. First one is autograft, which some a graft is obtained from the patient himself. It means his own body. Autograft is taken, placed inside his own body. Now allograft is the second method wherein graft is obtained from some donor, means other than the patient. So there is a chance of rejection because the graft is obtained from some other human being. Then there is a technique known as xenograft. The graft is obtained from the other species other than human being. If a human, suppose some organ of pig or some goat or like this is implanted inside the human body, then that is known as xenograft. And the last one is alloplast. Alloplasty is basically the creation of synthetic composite grafts using artificial means. So there are many other techniques available for producing this bone scaffolds, like deep freezing or the um, foaming process, or many other processes are there, but they are not able to produce the exact pore size that are required, or the exact porosity, calculated porosity we can say, or the customized shape. They cannot produce in that way. Whereas this additive manufacturing process can develop controlled porosity as well as customized shapes. That's why it is becoming popular. Right. So here in example of customized scaffold, how it works. So initially a CT scan of the, suppose this is a cancerous bone, and so first of all a CT scan is performed, and using CT scan they create a CAD model, so they can see a cancerous tumor there. So now they, in CAD model itself, they remove this. Okay, this is surgery is being performed, and they have removed that much portion of the bone. Now that portion, that cancerous tissue or cancerous tumor is removed, and the remaining part has been again CT scan, and the same CAD model is recreated. Now that CAD model is printed using 3D printing process in this way. So only that removed portion is printed because it will fix exactly to the left side. So in this way, implant can be, just a minute, customized implant may be produced, and that implant was actually the porous. That's why that has been kept in scaffold category. Here is another example of porous implant. This is implant, but this is porous. This has been porous. Like we can say topologically optimized, or we can say the lattice structure is there. Certain lattice structure is there. So strength is there, whereas weight, it is lightweight, light in weight. At the same time, it can bear the adequate strength. Then the next category is customized tools and surgical guides. This is broad category of auxiliary equipment that would be expensive and time consuming to make conventionally in small volumes. Because customized tools and surgical guides are very specific to individual patient, and to make using conventional process, they may be very costly affairs. So 3D printing technology can be used for this specific purpose. And for a specific task, a specific type of devices and tools can be fabricated, as you can see on the screen. This surgical guides can also be printed using 3D printing technology. Or the if we want to make certain holes in the bone, then this kind of fixtures can also be printed. Another category is health monitoring and drug delivery. So 3D printing is also useful in this a particular area by providing the customized drug doses. With the application of this, with the by using this 3D printing technology, we can create a customized dose of the drug, or we can fabricate a specific tablets, specific with specific composition. Whereas we know that pharmaceutical companies produce in specific compositions only, but we can here customize the doses of the customized drug delivery devices can also be printed. Then ingestible devices for health monitoring can also be produced using 3D printing. That has already been produced, and maybe are being utilized in some of the cases. Customized wearable health monitoring devices can also be printed. Ingestible devices means such kind of devices may be kept inside the stomach of a human being, and it can be used to send some data of the patient on a regular basis. Okay, here is an health monitoring and the drug delivery example of this specific area. So another advantage of additive manufacturing is the ability to make complex micro devices that work inside the body to deliver medicine or to monitor a patient's health. So an ingestible device that can remain in the stomach for a month, self-powered, it delivers discrete amounts of drugs for patients requiring long-term care, such as in treatment of cancer or HIV. So such micro devices will soon be able to transmit data wirelessly to an external medical variable for detailed health monitoring. Right. Then the in medical, this is the future of tailor-made tissues and organs. Right. So what is bioprinting basically? So we all know that the thousands of patients are waiting for various organ transplant worldwide nowadays. Many of that a patient cannot survive till he wait, okay, till he waits for the donor. So in such cases, bioprinting may prove a boon for these patients. Bioprinting basically make use of a bio ink at the place of engineering material. As we have seen earlier that the in most of the cases we are using biomaterials or biocompatible materials, whereas in case of bioprinting we use bio ink instead of certain engineering materials like titanium or polyamide or some chromium cobalt or some PEEK or PMM. That instead of that kind of materials, it use uses bio ink. Bio ink. What is bio ink? Basically, it consists of stem cells, growth factors, and hydrogels. Right. So it is combination of these three things. Stem cells are obtained from the patient's own body. Right. Then there are certain growth factors are added to that, and hydrogel are also required to grow the cells. It creates a favorable environment for the growth factor in stem cells. So what is stem cell? Basically, we all know about stem cells. Stem cells are the foundation of every organ and tissue in our body. Stem cells are undifferentiated cells that can turn into specific cells as the body needs them. So stem cells are basically they can self-renew themselves and differentiate themselves. Right. First they can renew themselves and then differentiate themselves. Stem cells are basically the most basic cells of any human being or any animal. So that cells later on when a human being grows, then they differentiate themselves into different specific types of cells, like they may convert themselves into bone cells or the epithelial cells, or we can say bone cells or some other brain cells or the liver cells or skin cells. So they can differentiate themselves into different types of cells, but initially cells are there when embryo is there. In embryo initially stem cells. So you may be aware that many people nowadays they have um, so there are different types of stem cells: embryonic stem cells, adult tissue cells, mesenchymal stem cells, and induced pluripotent stem cells. Different types. These are four different types of stem cells, where in embryonic stem cell is most common one. What they are, let us see. Embryonic stem cells are basically cells include within the embryo, the fetus or the umbilical cord blood. So embryonic stem cells are pluripotent, meaning they can give rise to every cell type in fully formed body, placenta, and umbilical cord. Right? These are the cells which can renew themselves, and later on they differentiate themselves into different types of cells in human body, specialized human cells in body. So let us not go into much detail into these cells. These are different types of cells available in human body. So how bioprinting works? Bioprinting is an extension of 3D printing or additive manufacturing that make use of cells, growth factor, and biomaterials to print biomimetic tissues, bone, blood vessel, and even whole organ in layer by layer. So how it works? It exactly works as additive manufacturing works, but here the raw material is different. Raw material is human cells basically. So this is the process chain of the bioprinting. So initially bio ink spheroids printed onto layer of bio paper. Bio paper gel. This is hydrogel basically. Hydrogel bio papers are there. Onto that bio ink spheroids are there printed. So in this way, the different layers of the hydrogels are there and layers of bio inks are there. So in this way, sometime the cells bioink means cells in bioink grows and they start taking shape of a specific um, they and they starts taking shape of a individual organ. So and this then we obtain a final living tissue. This right. There are some bioprinters based on different technologies: is extrusion based bioprinting, inkjet based bioprinting, laser assisted bioprinting. Different types of printers are available. Of course, they are very more sophisticated than our traditional 3D printers. They are more sophisticated and most precise and accurate. Right. Of course, they are more costly as well. Then bioprinting, in recent development in bioprinting, like San Diego-based Orgonova, this is the company which is manufacturing bioprinters. The first commercial bioprinter company has tried printing skin tissues, heart tissues, and blood vessels, among other basic tissues. A research team at Swansea, UK, has developed soft tissue and artificial bone for eventual use in reconstructive surgery. Another research team at Wake Forest Institute of Regenerative Medicine created functional artificial bladder and kidney. Research group at University of Pennsylvania tried creating vascular network using sugar template. Sugar template was dissolved once network was fully grown. So, meaning to say that there are many research groups working on 3D bioprinting, and they are trying to create different human organs. So far, they have got certain success in printing certain organs, but still there are many challenges. Like vascularization is one challenge that need to be overcome now, because just making small veins inside the human organ is very difficult, and researchers are trying to do that. Okay, here is the challenges. Current challenges: resolution and speed is one challenge, and bio-ink viscosity is another challenge. Then limited range of biomaterials, choice of cell source. Sometimes the human being, because of the age of the patient, the cell source may not be available, or the required cells may not be available. That's why people have started preserving their stem cells. Mimicking natural vasculature, this is again very important. Expensive in comparison with regular organ transplant. Since this is a relatively new technology, so this is very costly nowadays. Many ethical issues are also there. A specific policy, government policy need is required there. So these kind of challenges are there. Then there are some biocompatible materials. Yeah, I don't think so. There are so many biocompatible materials ranging from the polymers to metal and some other materials like mean metals, stainless steel, titanium alloy, cobalt, chromium alloy, magnesium alloy. These all are biocompatible and suitable for additive manufacturing process. Then advanced bioceramic material like alumina, zirconia, calcium phosphate, bioceramics, etc. are there. Then polymer ceramic composites are also there. Polypropylene tricalcium phosphate, PCl, polycaproelectron, hydroxyapatite, like peak, polyether, ether ketone. So many materials are available, biocompatible material. PMMA, polymethyl methacrylate is again very important material, biomaterial. So these are some of the biomaterials. And quickly, if we have 5 minutes, then I can quickly show you the facilities available in our university. We have got two 3D printing machines in our lab. EOSINT P395 machine, this white one you can see on the screen. This is a SLS printer, selective laser sintering printing machine. And this gray one is Jet Printer 450. That is ceramic based printer basically, Jet Printer 450. Many softwares we have like Magix RP, RP Tools, Jet Edit, Jet Print, Creo, Element, SolidWorks, Abacus, etc. in our lab. These are the printed parts through SLS machine. Here is the part fabricated via this Jet Printer 450. This is capable of fabricating color parts as well. And this is the research work done by our BTech student, one of my student. He has published one SCI paper on this. He created a CAD skull model using the CT scan data, and then he created one implant onto this and created this implant. We printed this. This was only for um, practice purpose, how this process takes place. So these are the photograph of the implant we design. Then we also printed one pelvic bone implant using some softwares. Geomagic software was there, SolidWorks was there. So in this way, we printed this model of this pelvic bone. Apart from this, I also worked on a MPCST sponsored project in which we printed certain scaffolds, bone tissue engineering scaffolds. So we performed various experiments for the uh, balancing the pore size and strength of the material, and we got them. CT scan. Also, we conducted some cytotoxicity test and found that the material was biocompatible as well. This is again one of the work of one of my BTech student who created a wrist splint using 3D printing technology and 3D scanner. So initially he scanned the wrist of a person, then he created a CAD model, then he modified that model into splint, and that splint is printed using our selective laser sinter printer. So this was about the medical and biomedical applications of additive manufacturing. And that's all from my side. Thank you so much for your nice patient hearing.
Sir, there is
Thank you.
questions from the students. First one,
Yes, yes,
which
please.
cells are commonly used in bioprinting?
What kind of cells? Basically, stem cells are used. Basically, stem cells are used for bioprinting. And because stem cells are the most basic cells, as I told you, they are very basic cells, and they have capability to differentiate in any kind of specific cell. Like if we want them to convert into, say, for example, the skin cells, then they can differentiate themselves into skin cells. Then they can convert themselves into brain cells like that. But still, apart from stem cells, it is not likely that stem cells are the only option. Other cells can also be directly used. Suppose we want to create a wrist or hand of a human being, then directly that kind of cells can be used.
सर जैसा अभी तक whatever my knowledge is, the stem cells से हम सिर्फ उसी बॉडी का ऑर्गन बना सकते हैं जिसका हमने स्टेम सेल कलेक्शन किया है.
Yes. That's what I am telling कि पेशेंट का ही स्टेम सेल होना चाहिए.
सर
पेशेंट का ही स्टेम सेल हो.
स्टेम सेल
Yes.
जो है ना जो हम बर्थ के टाइम पे स्टोर करते हैं फ्रॉम द
हाँ, स्टेम सेल बर्थ के टाइम पर जो स्टोर करते हैं, क्योंकि उस समय स्टेम सेल की क्वांटिटी बहुत ज्यादा होती है हमारी बॉडी, राइट. और जब हम ग्रो कर जाते हैं, जब हम यंग मतलब एडल्ट हो जाते हैं, देन इन दैट केस स्टेम सेल्स आर नॉट देयर इन दैट मच क्वांटिटी. तो इन दैट केस आप उसको स्पेशलाइज सेल्स ले सकते हैं. अगर किसी को बोन मैरो चाहिए, बोन सपोज किसी को बोन कैंसर है एंड वी वांट टू रिक्रिएट हिज बोन, देन उसका बोन मैरो ले सकते हैं इफ इट इज फाउंड सुटेबल. मतलब जो स्पेशलाइज सेल है उससे तो हम बना ही सकते हैं. बट स्टेम सेल जो है वो हमारे पास बहुत ज्यादा फ्लेक्सिबिलिटी होती है. वी कैन डिफरेंशिएट दैट इनटू डिफरेंट काइंड ऑफ सेल्स.
सर थैंक यू सर. एक अनदर क्वेश्चन है फ्रॉम स्टूडेंट साइड. व्हाट इज द स्कैफोल्ड?
Scaffold, okay. Scaffold is basically a structure like it is a porous structure just to provide support. Suppose our bone is broken and we have certain cavity. So in that cavity, we can insert a porous structure. Is required porous structure that is known as scaffold. जैसे हम बिल्डिंग बनाते हैं, कंस्ट्रक्शन करते हैं और उसमें बहुत सारा स्केफोल्ड लगाते हैं, स्ट्रक्चर लगाते हैं सपोर्ट के लिए. सो दैट इज एक्चुअली स्केफोल्ड. स्केफोल्ड उसको भी हम बोल सकते हैं. बट स्केफोल्ड यहाँ पे जो हम यूज कर रहे हैं, दैट स्केफोल्ड must have certain porosity so that if we seed some cell, then cell must grow inside those pores and those pores should be open ended. मतलब सारे के सारे connected होने चाहिए so that they can, so that the oxygen and other the nutrients should flow inside it. They are the porous structure basically.
Thank you, sir. Thank you very much, sir, for such an informative and inspiring session. Your valuable insight has certainly enriched our understanding of emerging dimensions of additive manufacturing and its integration with advanced technologies. On the behalf of Department of Mechanical Engineering, GCET, I express our sincere gratitude to you for sharing your valuable time, knowledge, and experience with us. Thank you once again, sir. Thank you very much.
Thank you so much. Thank you.